What up, coders? Today we're diving into the fundamentals of sorting algorithms. So the next couple videos will be all about them. We've talked about a few sorting algorithms, but they were kind of like niche ones, and now we're talking about just general sorting algorithms. And today's video, from the title and thumbnail, you probably know is the bubble sort. It may not be the most efficient, but its simplicity makes it a great starting point for anyone new to sorting algorithms. Remember, understanding the basics is the key to mastering more complex topics, so let's get our hands on some code. And by code, I mean talking about where the term bubble sort comes from. So, as you can see, the prompt for this bubble sort just says take an array and sort it. So I'm not going to be running like 15 different tests on this thing and edge cases, because we're just going to be focusing on the actual logic of the algorithm. And we're going to focus more on its time and space complexity and some trade-offs, aka pros and cons, to it, because that's more important. But if you're curious, the name of the bubble sort comes from the largest unsorted element bubbling up to the top as its correct position in each iteration of the algorithm. So you can imagine like having a container of liquid. The larger bubbles will rise faster than the smaller bubbles. In a similar way, the bubble sort larger values rise to the end of the array faster because they get swapped with smaller values. So as a result, the larger values end up at the end of the array, just like large bubbles end up at the top of a container first. So that kind of visual metaphor of bubbling up to the correct position is what gives bubble sort its name. So we're going to think about this with an analogy. I was talking to my wife right before I started recording this video, and she liked this analogy, so we're going to go with it. Because I told her, imagine you are a computer trying to sort a bookshelf of books. Like, ignore the human aspect, going, well, I'd find the tallest book and put it at the end. Not doing that. So we're going to arrange a bookshelf in ascending order of their heights from smallest to largest. We're going to start the leftmost book. We're going to compare it to the book next to it. If the left book is taller, aka greater in terms of height, we swap. Then we move on to the next and compare the books, the second and third book. And we basically compare their heights. If the right one's taller, it stays. If the left one's taller, they swap. And basically we keep doing that until we reach the rightmost end of the bookshelf. By the end of that process, we'll have the tallest book. We'll have bubbled up to the rightmost end of the shelf, aka the end of our array, since it was swapped every time it was found to be taller than the book next to it. Then we repeat that process all the way from the beginning. You can see what the efficiency problem is. All the way from the beginning up to, but not including the end, because the end theoretically has the tallest book on the bookshelf. So then we do the same process, compare, swap, compare, swap, compare, swap, until the second tallest book is next to the tallest book, and then we iterate from the beginning all the way to the end except for the last two spots, and we keep repeating that pattern until we have an entirely sorted bookshelf. And I have a little YouTube video at the end that shows y'all how it works. So let's actually dive into the code, because you'll find that it's not that terrible to implement. And again, the concept of understanding this simple, inefficient sorting algorithm is far more important. This is one of those things that, just like I mentioned a moment ago, I told my wife off camera that, this is one of those things where you're not going to be coding it on the job. You know, this is one of those things you might learn in a computer science course. And it's one of those things that you're probably going to get asked it in a beginner's interview because, well, like, you know, it's one of those classic interview questions for a reason. And being able to discuss its time and space complexity, and upon the finale of my little sorting series here, you can have some other sorting algorithms to compare it to and to discuss their benefits of, right? So let's dive on in finally. Because I'm going to be using it more than once, I'm going to choose to make a quick length variable. And you know, I should have mentioned, function bubble sort takes an input array. It's going to be we're going to imagine it's an array of integers that are unsorted, or we're going to assume to be unsorted, and we're going to sort it as the output, right? So just getting that out of the way. But like I said, we're going to be using our array length more than once, and for simplicity and readability, I'm going to go ahead and put it in a variable, even though I don't normally do that all the time. From here, we have to iterate from every single book starting at the beginning to the very end multiple times. So we're going to have a nested loop structure. So we're going to have our first loop start with an iterator of I, starting at position 0, no surprise there. It is going to continue until we get to the length of our array, and then we're going to iterate by one book at a time. The inner array will act as our comparison of like being one book ahead, so we can then look at our current book, our next book, and swap them as needed, right? So this inner array is going to be the sorting to the very end every single time, that will then subtract 1 each time the outer loop ticks. So here we go. What I mean by that is the following. We have to use another variable name other than I for our inner loop here. So we're going to choose to use j, the classic j. Shoot j, shoot it. We're going to have a j of 0. And j is going to continue for as long as the length. Okay, remember? I mentioned the sort is we don't have to go all the way to the end of the bookshelf every single time. We have to stop one short of where we were before. This can be calculated by taking and subtracting I from the current length, how many times we've iterated through every single book, minus 1. That math right there will check us out to make sure that we are always stopping like one more than we did on the previous iteration. So again, the first iteration means we'll end it where we are not going to the very end because the largest book should now be at the end in our analogy. And then as I increments every single time we go through our comparison and swap, then it'll keep going less and less to the end. Okay? From there, we have to obviously iterate j by 1 because again, like it's like moving in tandem here. So what we're going to do is say if, like I said, if the left hand is bigger than the right hand, we swap. So where we're going through array j, if it's bigger than the one on the right-hand side, it is time to swap. And we're going to swap by using a quick temporary variable. So I will say let temp equal array j. From there, we're going to take the current value of rj and assign it what it was on the right-hand side because it's smaller. And then we're going to go to the right-hand side, aka j plus 1. And assign it our temp value that we were holding because now we have basically swapped the books. So this is holding the book to swap it. This is the logic to swap the two books because the left-hand one was taller, so we need to swap them in place. This is what we do. Then from there, we simply continue this inner iteration. So it'll go all the way through, stopping with theoretically the largest book at the very end. Then it'll finish the inner loop. Then the outer loop will tick, and it'll do the next iteration starting from 0, and it'll go all the way to the top by going to next loop, I should mean. Then the inner loop starts again at the beginning and goes all the way up to, but not including, the last book, and it continues to do that with the second to last book, then the third to last book, then the fourth to last book, fifth, sixth, seventh, eighth. Continues on until we have a nice slope, right? A values of smallest to largest sorted in our array, which means after both loops are completed running, all we need to do is return our array as it should be sorted for us here. And that's it. So like I said, after each iteration of this inner loop, it'll keep sorting the next biggest thing to the end of the array. It will bubble to the end of the array by constantly checking and swapping everything in place. And then this outer loop ensures that we completely clear the array of the values until the very end where we have the sorted array. So yeah, like I said, the code itself, not that bad. So to TLDR, we're going to put the array length in a variable because, like I said, it'll be a little bit more easy to read right here instead of array.length minus I minus 1. Just a little bit of code clarity. And again, we don't need to, technically this will have to calculate it on every iteration. So this is kind of like a micro efficiency step we could take by having to calculate the array length just once and use that variable in place instead of an array.length in each position. The outer loop will iterate length times, right? The variable I is the counter for our loop right here. The inner loop will start and iterate length minus I minus 1 times. That's because, again, with each iteration of the outer loop, one more element is in the correct place at the end of the array, which means we only need to do one less comparison. So each time the outer loop ticks, we have one less comparison on the inner array, and that's that trick that happens there. Yeah, and then once again, we simply compare. If the left-hand element is taller or bigger than the right-hand element, we swap. This is your classic array swap logic with a temp variable. And then after everything is said and done, we should be left with a sorted array, and then all we do is return it, and we're good to go. So let's actually see if it worked here. I'm going to grab this bubble sort. We're going to console log the R and run this code, and theoretically, if I save it, we get 11, 12, 22, 25, 34, 64, 90. And congrats, folks. We got ourselves a nice little sorted array right here. Nothing to it, right? Like I had mentioned, I do have a video here that can help visualize what we're looking at. Let me swap scenes. Cool. Some of y'all might have already seen this before. It sounds awesome, but I'm not going to destroy y'all's ears with the sound it makes. But again, this is a nice visual, and I would like to thank Timo Bingmann on YouTube. This was uploaded like almost a decade ago, and it occasionally makes the rounds on our videos on Reddit. So I had this in my back pocket because I've seen it before, and I'm fascinated by watching it every time. So we're actually going to be using his videos right there. I'll make sure to put a link to his channel in the description below to make sure y'all can go check out other sorting algorithms visualized and audioalized. Because I think these videos are great and kind of show us how these sorts work and how efficient or inefficient they might be. So again, credits to them for this video. I'd like to give them a big shout out for being a part of my life even before I was a programmer. So yeah, this is a bubble sort visualized. So remember, we're going to see multiple iterations that will simply be going one less every single time. And we're going to see this element stuff sorted out here. It's only a minute long. I'll try not to leave too much dead air. But as you can see, the largest values are bubbling up to the top here, right? And that length minus I minus 1 is this part in action where we're having to not go to the very end. We're going one less iteration each time in this bubble sort. But as you can see, this is where the inefficiency is, because you can see how many times that inner loop is having to traverse the array of values that we have left as the outer loop ticks. And as we get to the end, we're just, again, bubbling up the largest remaining elements to the right-hand side, the end of the bookshelf. Going. We're almost there. Let's go. Like I said, if the audio is on, it sounds really funky. And again, this is exactly what our code is doing. Just compare, swap until we are sorted. And that's what the bubble sort algorithm does for us. Awesome. So yeah, that's what we're doing. That's what the array is. That's what's going on there. And in terms of big O, right? Because this is where you're going to, again, like you may not even be asked to implement this in an interview, but being able to discuss it and pros and cons is the more important part. So as always, we have a big O. We have a time complexity of, I believe, big O of an n squared, meaning it's a quadratic. Because this is and I should mention this is a time complexity for the big O, because at the worst, in average cases, when n is the number of items being sorted, aka our input array, it's because each pair of elements in the list must be compared, and these comparisons are repeated for every element as we saw in that visualization, and result in a quadratic time complexity. And if you recall, the big O of n squared is that yellow line right here. It's the number of operations will skyrocket very quickly the larger our input array is, because of that constant rerunning through the array and constantly comparing all items. However, it has a big O space complexity of 1 because it's an in-place sorting algorithm. You see, we don't create a new array for it to be returned. We simply sort the array we were given and return that array we were given as a sorted value. So because it doesn't require any additional storage space to perform the sorting, it's a space complexity of big O of 1, which makes it quite space efficient, right? So again, even though this is a inefficient time complexity, it's a good space efficiency, and also fairly simple to understand the logic of and write, hence why you could kind of leverage that knowledge in an interview should it come in place. So again, super simple, very space efficient, and honestly, and also detects where the list is sorted. So the bubble sort has the ability to detect whether the list is already sorted, because after one full pass, if no swap has been made, it means that the list is sorted and the algorithm can terminate early, right? That's the benefit to the bubble sort. If you have a sorted input, it just goes zooms through. It made no swaps, and it's like, well, okay, we're done. But it is very time inefficient, like I said. It's not optimal. The other ones like quick sort, merge sort, heap sort, they all outperform it, making this less of a practical algorithm you would use in the real world. And it has tons of swaps. I mean, you saw from that video, and imagining as I described the whole bookshelf analogy, this has a ton of swaps and tons of operations, and it can be expensive because of that. So it has its uses, and it's mostly as like a teaching tool to the basics of sorting and how to begin approaching different kinds of sorting algorithms. This is the most simple one that you can understand from a programming perspective, in my opinion. And you don't really see it in real world scenarios because of its inefficiencies. But again, it is cool because it's a teaching tool. It helps you understand efficiency a bit better. It starts giving you the terms and ideas and pictures in your head of how you can begin to talk about efficiency. And we'll have more discussions about that as I show you other sorting algorithms. It's very stable. I mean, yeah, it's gonna it does in-place sorting, which is another big pro to it as well. So even though it's not used a lot in the real world, it's still cool to know and cool to learn. So, I mean, as always, y'all, I would like to thank y'all for watching. And again, any kind of uh, we're trying to become better developers in our journey together here, right? So if you enjoyed the video, give us a thumbs up. Consider subscribing to this lovely channel for more videos like this. And I'd love to hear y'all thoughts on, again, there's not really like another way to code this. So comments wise, hopefully I've illuminated something for y'all, or if you have code pens of other sorting algorithms that I'm going to get to, go ahead and start linking them down below and check them out. Because remember, constructive and positive comments are the ones that are always welcome here. And let's keep the discussion going to help each other grow better. So thanks for tuning in, and I'll see y'all in the next video.